In this how-to video we're going to look at the rate determining step for a chemical reaction and how by knowing something about the rate determining step we can actually predict a reaction mechanism, in other words how the reaction proceeds and how the species in the chemical reaction interact with each other from reactants to products. So the first thing to know is what is the rate determining step, and we need to remember that chemical reactions don't always take place in one go. In other words, A reacting with B doesn't necessarily go to C and D in one step. It can often happen in a series of steps, and this is called the reaction mechanism. So, assuming that the chemical reactions happen in a series of steps, the actual overall rate of the reaction will be dominated by whichever step is the slowest. In other words, if there is a step going at 30 miles an hour, well, the overall reaction can only ever go at 30 miles an hour. And that particular step is called the rate determining step. It defines how quickly or how fast a chemical reaction is going to go. So, a reaction mechanism is a series of steps in a chemical reaction pathway, and it is governed by the rate determining step, that step which sets the speed of the reaction and is the slowest step in that chemical reaction. The best way of explaining this further and in detail is to actually look at a chemical reaction. And here is a chemical reaction between nitrogen dioxide and carbon monoxide, forming nitrogen monoxide and carbon dioxide. So if we actually look at the stoichiometry of this equation, that tells us that effectively 1 mole of nitrogen dioxide gas will react with 1 mole of carbon monoxide gas to produce 1 mole of nitrogen monoxide gas and 1 mole of carbon dioxide gas. But that equation doesn't tell us anything about how this reaction happens. In other words, it doesn't tell us how the nitrogen dioxide reacts with the carbon monoxide to make the nitrogen monoxide and the carbon dioxide. It doesn't tell us anything about how that reaction occurs. So to do that, what we have to do, or we have to have information on, is experiments about the rate of this reaction. Specifically, if we look at this reaction, what the order of the reaction is with respect to nitrogen dioxide and carbon monoxide. And it's from that information that we can determine what is the rate determining step, and then we can take that forward to propose a reaction mechanism. So, looking at this reaction then, what I've got here is some results from experiments carried out, and we find that the reaction is second order with respect to nitrogen dioxide, and it is zero order with respect to carbon monoxide. So our overall rate equation is rate equals the rate constant times the nitrogen dioxide to the power of 2. So let's proceed further with this experiment. If we look at the rate equation, we can see that we have nitrogen dioxide to the power of 2. And this is effectively the rate determining step. It's this which governs how fast the reaction goes. And what this is basically saying is that anything which appears in the rate equation is involved in the rate determining step. So in this case, the rate determining step, the step which governs the rate of this chemical reaction, has nothing at all to do with the carbon monoxide. It has only something to do with 2 molecules of nitrogen dioxide. And if we were to write this down, we would see that the 2 molecules of nitrogen dioxide must go on the left hand side of the equation for the rate determining step. So if we're going to work through a reaction mechanism, what we need to do is we need to appreciate that the first part of this reaction pathway involves 2 molecules of nitrogen dioxide reacting together in some way. So because we've got 2 molecules of nitrogen dioxide effectively reacting together, and this is the rate determining step, well then there must be another step, at least one other step, which drags in the carbon monoxide, because carbon monoxide and carbon dioxide appear in the overall equation for the reaction. So what I'd like to do is to propose a 2-step mechanism for this reaction. We know that the first step, the rate determining step, is the slowest, but then there is another step, a second step, whereby which is a fast step, which takes us to our overall equation for the reaction. So it's very helpful if we write it down in this manner. Here's our first step, and here is our overall equation for the reaction. So from these 2 equations we can now start deducing some of the things which will fit into the products of this first rate determining step and the second step. And the first thing we can say is, well, carbon monoxide and carbon dioxide must be involved in the second step because they are in the overall equation. So we've got to have carbon monoxide here, and we've got to have carbon dioxide here. And what else can we say? Well, nitrogen dioxide must be a product of the second step because 1 molecule NO2 is in the overall equation. So what do I mean by that? Well, we've got 2 molecules here, haven't we? And we've got 1 molecule here. So one of the products here must be nitrogen dioxide because effectively we have a cancelling out. What we're going to do is we're going to add downways to get the products. So what we have 2 here and we have 1 here. So we must have 1 NO2 over here to effectively cancel out one of the NO2s over here. So let's stick on that piece of information. Here we go. Here's our first rate determining step, the slowest, and I've added onto it basically what I've said here, which is carbon monoxide must be in this second step. Carbon dioxide must be a product in this second step because it's in the overall equation. Another product in the second step must be NO2 because we have 2 NO2s here and we've only got 1 NO2 in the overall equation, so one of the products over here must be NO2 because we want to cancel out one of these NO2s, so we only effectively have 1 on this side of the overall equation. So the other reaction in the second step must be NO3 because if we look at the stoichiometry, we've got CO, N, O2, CO2. We need a nitrogen and 3 more oxygens on this side to get this equation to balance. So the other reactant here must be NO3, but there is no NO3 in the overall product or the overall equation. So one of the products of this first step must be NO3, because NO3 over here will cancel out NO3 over here. And of course the other product of this reaction overall is NO. So we know now the products of the first step. One of them must be NO and the other must be NO3. NO3, NO3, NO. And the NO3s will cancel out. One of the NO2s will cancel out, and the NO will fall into the overall equation. So let's add that. And there we go, the complete mechanism. First step, NO2 plus NO2, giving us NO and NO3, which is the slow rate determining step. And then the second step is the NO3 now reacting with the CO, carbon monoxide, to form NO2 and CO2 to form. So, adding these together, we've got NO2, CO, NO and CO2. The NO3 is cancelled out with the NO3, and one of the NO2s is cancelled out with one of the NO2s to give us the overall equation for the reaction. And finally, the NO3 is actually known as an intermediate. And an intermediate is a species that's generated in the first step of a reaction mechanism, but is consumed then in the second step. So it does not appear in the overall equation. In this case, the NO3 is an intermediate because it is produced in the first step and it is consumed in the second step. And typically intermediates are very, very short-lived. This NO3 gets used up very, very quickly in the second step of this reaction, which is the fast step. And that's it. Quite a difficult concept, but by setting it out in this methodology, it becomes far easier to rationalise and understand what's happening. I hope that's been helpful. Thanks.